Okay. So this will be the continuation of the index theory talk. So this is part 2. So just a reminder or like recap of what we were doing last time. Last time I had defined what were vector bundles. So defined so vector bundles were just a family of vector spaces. So examples, family of vector spaces over manifolds. Examples were like just trivial bundle over the circle. So this in a better picture, this just looks like a cylinder, infinite cylinder. This is one example. Then there was also the example of the Mobius strip. How do I draw this? Something like this. Actually, no, let it be. So Mobius strip was you take a piece of paper like this, you identify these two ends in the opposite direction and glue them together. So it will close up and there will be a rotation. So that will be the Mobius strip. One example, second. This is S1 cross R. And in general, there were other trivial bundles, which is S1 cross RK. Sorry, M cross RK, where M is any manifold. And in general, I had said, if you have a vector bundle E, there is a projection map down to the manifold, which will be called pi. And if you take any point P here, and you look at the inverse image of P, this will be called EP. EP will be a vector space of, it will be isomorphic to some k-dimensional RK. Right, so those were bundles. And I also said what a section was. Section is nothing but you have a bundle, you have the projection map. Section is nothing but a smooth map like this, so that you commute this way. Or in other words, I want to say, if you take any point P here, S of P will be some point over here. And that will be exactly belonging to the vector space EP. It will be some vector in the vector space EP. Right, so over P, it will always be inside EP. So if you change to P prime, it will be inside P prime. Okay, so that's why it's called a section. With so those are sections. So these are sections. I also defined connections. Connections were a way to differentiate these sections. So way to a way to differentiate sections. So if you, so this will be denoting the sections. This is sections of E. When I say sections, I'll just mean smooth sections. So a connection is a map which takes vector fields on the manifold. So these are vector fields, and it will take a section and it will give a new section. The notation will look like this. So X will be the vector field here. S is the section. This will be mapping to this. What you should read this as, you should read this as S, and you're differentiating it in the direction of X. So X was a vector field on your manifold. You move in that direction and you differentiate, and it is defined in some way. So don't worry too much about this. So vector bundles also had local trivializations. Local trivialize. What this means is there will be some open set U here. Yeah, there'll be some open set U here such that this is isomorphic to V cross RK, right? Where if you take the projection of this here, it will go into V, a subset of M. So there's an open set here on E, which is called U. When you take the image down to here, it's V. The image will be V. And what I'm saying is locally around every neighborhood or every point, you'll have such a structure. So basically, you are saying the vector bundle looks like manifold cross RK everywhere locally. Okay, so these are called, let's not say what they are called, but now since you have such a thing, you can choose bases here, and it kind of fixes bases for each of the vector spaces here. Right, so fixing a basis here and changing the point will give you different bases for each point here. Okay, it's a sort of smooth way of fixing bases locally. So bases for each of the EPs. So by doing this, what happens is what we did was the connection gives rise to a matrix. So you get a K by K matrix like this, and each of these entries will be one forms. So maybe if I write it better, these will look like omega ij or alpha ij, where alpha ij belong to one form on M. Okay, so only when you have a local picture, basically once you fix a basis, you can talk about the connection as a matrix like this. And these were matrices of one form. Using the connection, I had also defined what a curvature was. Curvature is curvature. Curvature takes in two vectors and it differentiates your section in the following way. Okay, so this is curvature, and why this is called curvature we'll not get into. And this formula also not very important. You just need to know what this is measuring is. If this is non-zero, it just means how far is this commutator from this commutator. It's just measuring that. Or in other words, it's measuring if you differentiate in one direction and in the other direction in different orders. So if you do x1 first, then x2, and x2, then x1, what will be the difference? That's what this is measuring. Okay, so that is curvature. Again, locally, curvature gives curvature R gives a matrix of K by K forms, omega ij, let's call it. So these omega ij's now will be two forms on M. So these are forms on the base manifold, and they measure the curvature locally of your vector bundle. And what I had said this, let's say this was omega. If I do a change of basis, then omega prime in the new basis will just look like T omega T inverse, or T inverse T omega, or omega T something. So basically it turns changes like this. Now, if I had a polynomial of this matrix, for example, the determinant, example determinant. So if I take the determinant of omega, this is a globally defined thing. Is a L2K form. Why? Because if I looked at determinant of omega in a different representation or in a different chart, I will look at it as T omega T inverse. But determinant, when you have T and T inverse, it just goes away. Okay, so you have determinant of omega. So regardless of what representation or what basis you chose to represent omega, determinant omega will always be the same. So this is why you can define this as a globally well-defined 2K form. Okay, and we had a theorem. So polynomials which satisfy such a thing, which is if I put a polynomial of this, it is kind of invariant under these two. Those are called invariant polynomials. Determinant is one example. There are many other polynomials. I will not go too much into it, but if you're just thinking right now, you can just think of determinant as the only one. There was a theorem which says determinant of omega is closed. That is one. So this will give a cohomology class. So this will give a cohomology class, and belonging to H2K of M in the base. This is independent of the connection. So basically what I mean is if you chose another connection, this class, this cohomology class will still be the same. A priori, this always depended on the connection. Maybe I will write it in a better way here. So it is the determinant of the curvature. This form depends on the curvature or the connection, but the cohomology class does not depend on it. So essentially what this is just a invariant of the bundle. So determinant of, so there were no choices involved in defining this. So this is an so it's an invariant of the bundle like this. Right. So this is this can be defined topologically, or this is called a topological invariant, and this is an example of a characteristic class. Characteristic class. Okay, right. So this is what I had done till last time. Were there any questions for this? Okay, so today I will just define what K theory is. So the K, or let me just say K theory. K theory. What I'm trying to do is, the goal here will be, the goal is, or let me say first that, so suppose I had two vector bundles, E and F. I had, we can do a addition of these. So we can perform addition. So which is tensor, whatever, direct sum. So you direct sum each of the fibers, each of the fiber vector spaces, and that will build up a vector bundle for us. Now what my goal is to make this a group operation. So the goal is to make this direct sum so in particular, what are the properties I'm looking for? First of all, in my group, what I want to do is I don't want to treat isomorphic bundles as the same. So I want to define some equivalence class. So don't want to treat isomorphic. So we don't want to treat isomorphic bundles differently because we are trying to capture the topological interesting twistings that are in these bundles. We are not looking for the trivial stuff. As in, if two things are same, we don't want to keep them as two elements of our group. Okay, so we want to keep isomorphic bundles as the same. If we want this to be a group, we want cancellation property. So even to like make it into a group to start with, to define subtraction, we need a cancellation, as in if E, F, G are bundles, then we want to say if E is equal in some sense in our group thing, we want E plus G to be equal to F plus G as well. So basically, I want to somehow say I can cancel things off, right? Without that, there's no way we can do subtraction, right? So I will define it saying define, or maybe not yet. So let's say I will say E and F are similar if there exists G such that E plus G, F plus G. Right, so this is isomorphism, vector bundle isomorphism, and in particular, it takes care of this also. If you can just take G to be just a trivial bundle, trivial zero-dimensional bundle. So we have set an equivalence like this. These will be treated as the same. So once you do this, how do we define subtraction? So for the example, let's say we take natural numbers. Let's say natural numbers union 0. How do we define the set of integers just using this? One way to do this is look at the products where m and n. Look at m and n, just tuples of these, and you say two things are equivalent if m minus n is equal to m prime minus n prime, but minus is not defined. So I will just say m prime equal to, m plus n prime equal to m prime plus n. Okay, so saying this is the same as saying this, right? So I will say these two are equivalent, these two are the same integer if this happens. So if you do cross addition, they should be equal. So that's how you make integers out of the natural numbers, because there is no negative numbers. This is what you do. We will do the same for vector bundles also. So what we'll do is let E, F, E prime, F prime be vector bundles over. So it's over the same manifold. I will never change the manifold. So we will say that E comma F, this is the same as E prime comma F prime if there exists a G such that, so from the previous, I wanted this to be isomorphic to E prime plus F, but now I want cancellation, or just I want to ignore some triviality, so I will also add these. So basically, this will be my final equivalence relation. So now if you look at the equivalence classes of the pairs, so look at all pairs E comma F modulo the relation we have here. So this will be the K group. K group. So this is the 0th K group. There's also 1, 2, and 3 K groups, but I will not say that here. So it is all E and F vector bundles, comma F bundles over M over the quotient. Right. So now, because of how I have defined, this will be a group. So you can do group addition where two elements you add by adding these two and these two, and subtraction also just by flipping and adding them and whatnot. Right. Okay. Question still here. Okay. So this is just the K group. There is also a relative version of K group, which I actually need, but I will not define. So it like in relative cohomology or homology, we have H0 of M. We can also talk about H0 of M comma A, where A is a subset of M. Basically, what this does is, this just means we are ignoring everything that is happening inside the subset A. We are just we just care about the topology in M, which is not inside A. You can, another way of thinking this is, you can just quotient all of A. So basically take all of A, collapse it to a point, then look at the homology of that. In some cases, this will be the this will be isomorphic. It's not always, but in some cases, in most cases, let's say. So relative K groups also will be the same thing. So relative K group. So relative K group, it will also be denoted like this, where A is a subset of M. And what I will say is, you will have the same things, except on the set A, so E and F, you also need a third thing, phi here, where phi is a map from E restricted to A to F restricted to A, is an isomorphism. Okay, so that will be your set. And again, there'll be the same similar equivalence relation that will make it a group. So basically, I'm saying we are looking at vector bundles, which on the set A will just cancel each other out. Okay, so there is, it's just, it's, read it as it is trivial over the set A. Okay, so that is relative K groups. That is, I don't know if I will get to it too much or not. So we will just take a slight different path for now. We will define what are differential operators. So these are just independent of everything I've said, but it will link back in some way. A differential operator D will be a map which takes C infinity functions to C infinity functions M, such that in local charts, in local coordinates, differential of a function f will look like summation, how do I say this? Let's say alpha of x d to the mod alpha by d alpha or dx alpha of f. Basically, alpha is it's a multi-index notation. So alpha will be alpha 1, alpha 2, alpha 3, where d alpha dx to the alpha is nothing but x alpha 1. So alpha 1, alpha 2, alpha n will just be in numbers like natural numbers or even 0. And you're just differentiating that many times. T x. I should have this at the bottom, sorry. And x alpha, let's say k. Okay, so basically this is alpha 1, alpha k belong to natural numbers union 0. Okay, these are just natural numbers and you are basically differentiating in that direction. So x1, x2, x3, xn will be directions or coordinates on your manifolds. And you're just differentiating your function in that direction. And you'll also put some coefficients along with it. So these are differential operators. Examples will be if you're on Rn, just differentiate by any xi, or just take any combination of these. That will be a differential operator. A special differential operator, which is the Laplacian, is d by d xi. I keep writing it wrong. Xi, but you do it twice. So differentiate it twice, I equal to 1 to n. So this is called the Laplacian. And obviously you can think of a lot more than these. So these were differential operators on functions. And as I had said, you can generalize functions. Sections are a generalization of functions. So these are just sections of the trivial bundle. So you take m cross r as a bundle and you look at sections, those are C infinity functions. So instead I could have said all this, and I would have said D is a map from, if E is some vector bundle, I could just say this. So this is just to make it a general picture. If you don't like it, you can just stick with the C infinity functions, right? So here E to F, maybe I can do different things also here. So in such a situation, D will look like the same thing in local coordinates. A alpha of x, D by D alpha dx alpha, I guess, S. So here only caveat is A alpha x will belong to, it has to map something from E to F. Right, it's just it has to be a homomorphism from E to F. It's just you differentiate the coefficients first, then you kind of multiply it by a matrix and push it to the next vector bundle. Not very important, you can just ignore it for now. And the order of this operator, order of D is the max of mod alpha such that A alpha is non-zero. Okay, so that is it's basically maximum number of differentiation you're doing in D. Okay, so now, so as you see, I could only define these in local pictures. These coordinates do not make sense in a global term on a manifolds because you don't have directions to differentiate, right? The directions don't make sense. When you do change of coordinates, these will all change in a very weird way. Okay, so this is not a global picture, I can say. But what does make sense is if you change the coordinate in the top, only in the top order. So if you have, let's say, Laplacian, which is del square by del x squared plus del squared by del y squared plus del by del y plus maybe 1, something like this, some operator like this. So here, when you change the coordinates, what will happen is you will change x into something, y into something, and you will apply chain rule, and it will split out a bunch of terms here. And what will happen is only these parts will be similar. Like this part will be comparable to the one you changed in the new coordinates. But this will also spit out lower order terms, which will go into this, and these will not be comparable anymore. Only the top order parts in the new coordinate system will look similar. It won't be the same, it will look similar or comparable, but the lower order part, it just becomes a mess. So it's you cannot keep track of it. So what we will do is we will define something which will keep track of only the top order term. Okay, that is kind of done by doing, it is motivated by doing Fourier transforms. So what I will call is a principal symbol. Right, so now let's say we just took the same operator D. So let's just take this D. If I do a Fourier transform of this, one good property of Fourier transform is it takes derivatives and it changes it into multiplication by something. So Fourier transforms, you will have to evaluate it on C1, C2. So Fourier transform of D will be nothing but, or maybe I'll say df to make it even more concrete. So df f. Right. So this will be nothing but this will be, so if you're differentiating with respect to x, you'll put this. Then if you're differentiating with respect to y, you'll put 2. If you're differentiating with respect to y, again, it's just here. Then if it's just a constant, it's just a constant of c, something like this, or f hat rather. F hat is a Fourier transform of f. So this is what Fourier transform does to derivatives. It takes derivatives and it converts it into just multipliers. Okay, and that will be that is what I will use as a motivation to define this principal symbol, which will just be the principal symbol of D. It will be evaluated on C1, C2. It will just be the top order part, this squared plus this squared. Okay, so that's all the principal symbol is. So given a differential operator, principal symbol will just be this. Okay, if this was all done on Rn, so are there any questions till now? Because I'll just say this hand wave a little bit after this. Okay. Obviously, there are some constants I'm missing here. There are some I here and there, whatnot, but we will forget that. So now on a manifold, locally my D looked like A alpha x d alpha by dx alpha or something like this. So now I will just define my principal symbol. It will take two things. It'll take x, it'll also take c, where x is belonging to the manifold and c will belong to the cotangent bundle. Y, don't worry too much about y, it's for definitions. Basically, you can think of x as x1, x2 dot 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 xn, and c is nothing but c1 cn. Okay, and my principal symbol of D will be defined to be, I have to give x and c. It will be defined to be summation a alpha of x. A alpha doesn't change. It's only the derivative part which changes. It just becomes appropriate powers of c. The appropriate terms you take and take the power. So you're differentiating with respect to some xi, just take those ci. Okay, so then this just becomes this is no longer a differential operator on this these things. It just becomes a map from E to F. Okay, because only these are the things that matter. These are just polynomial multiplications now. These don't do much. Okay, so that is principal symbol, and I'll just claim here sigma D is invariant. So it's invariant under coordinate change. Or in other words, sigma D is a well-defined map from, it will be defined on the cotangent bundle, and it will map into form of E comma F. Okay, so it will take a cotangent vector and it will give you things here. Okay, so these are symbols of differential operators. Why we do symbols and all, it's basically one motivation to do one, not motivation, how do I say? Why we do this is we want to think of differential operators as integral operators. So want to think of operators as integral. In what I mean by that is, as I said, Fourier transform changes differentiation into just polynomial multiplication. So if I do a Fourier transform, then do a Fourier transform inverse, I should have the same thing, let's say for smooth functions, df. So here, Fourier inverse of d, but d had become, f of d became a multiplication operator. So this in fact became multiplication by some matrix, let's say A, which depends on D, times the hat of this. And Fourier inverse is nothing but an integral. So it is something like I C A D F hat of C D. Okay, so what I've just waved my hand a little bit, but this just means the differential operator D, I have written it in terms of integral of something here. Okay, F is just there. And whatever is here, which is not part of F, is the data I need to differentiate the operator. Okay, this is called the kernel. Kernel of this differential operator. So differential operator turned into an integral operator, and the kernel is basically telling you how to differentiate. Okay, so that is the idea of why I take why these are important for differential operators. Again, something very quick definition. So elliptic. Elliptic operators are just so D is a differential operator. Okay, such that for each xc belonging to the maybe I'll write it this way. Yeah. So you look at the elements of your cotangent bundle. So that will be a point and a vector, cotangent vector, such that C is non-zero. Then we want the principal symbol of D at this point and this C to be invertible, to be. So this sigma D, it will map from this to hom E comma E, or yeah, let's just stick with E comma E because I want to say it's invertible. So here I'm just saying if you take non-zero elements here, it should map to invertible elements here. That is what it means to say D is an elliptic operator. Right? Again, examples I had done, which was the Laplacian. If you look at the principal symbol of this, this will be nothing but I squared, or actually there's a modulus here. Okay, so that means if these are all non-zero, this will just be a non-zero number, which means it will be invertible. So this is elliptic. Okay. Okay, and fine. So those were differential operators. There is a theorem which I want to say, but before the theorem, I want to remark saying so gamma E, these were sections. We can induce inner products on this in some very simple way, and we can talk about and can. So these were smooth sections. I can talk about L2 sections. Once I have an inner product, I will say take measurable sections and see its inner product, and the norm should be 0. I can look at L2 section. So these no longer have to be smooth. Okay, but they can have discontinuities and whatnot. But the theorem is, which is called elliptic regularity. Elliptic regularity. This is if D is a differential operator, is an elliptic if differential, then we have certain properties for its solutions. So if let's say take some f, which is a L2 function or L2 section, you can think of it just as functions, and is a weak solution. So weak solution, what does it mean? Weak solution means I want to say it is df equal to 0. So that's what it means to be a solution. But I cannot apply D onto non-smooth things, right? Differential only is, as I defined it, was only for smooth stuff. So what I will say is I want the weak derivative to be 0. It just means I want f comma d star g to be 0 for all g a smooth function. And d star is an adjoint, it's a formal adjoint of d. So because we had inner products, you can always define formal adjoint. And you can give a picture saying this will also be a differential operator, which can be easily defined locally. So you apply it to G, any function G here, and that inner product with F should be 0. If this happens, then we call F to be a weak solution of T. Right? So now if we have any weak solution, the theorem says then F is actually smooth. Or in other words, I just want to say F belongs to smooth section. So what this is saying is, let's start with some section which doesn't necessarily have to have any nice continuity properties. It can just be some L2 function. And let's say it is weakly a solution of my operator. Weakly means it just satisfies such a thing. If that happens, then F will be forced to be smooth. That is why you need elliptic regularity. So that kind of just the top order part being invertible forces your F to be smooth. Okay, then that is one. Second part is the operator d star d. So this is also a new differential operator. This is essentially self-adjoint. It just means it's so it is a differential operator. So it's an operator between Hilbert spaces, and it is an unbounded operator. So you take its closure, which is defined somehow, is an so you take its closure, take the closure of this in some, it's defined in some way. That is a self-adjoint operator as an unbounded operator. Basically, what that allows me to do is it will give me a spectral decomposition of this, and I can do functional calculus of it. So, so we can get spectral decomposition and do functional calculus. Basically, what that means is I can say what exponential of d star will be, or sine of d star d will be. So basically, it allows me to define these operators. These will be new differential operators, and having self-adjoint things, you can do this because you'll apply this function to the spectrum of the operator, and that just gives you the answer. And finally, 3, D is Fredholm. Which means kernel of D, comma kernel of D are finite dimensional. Okay, that's what it means. Because of that, I can define something called the index of my operator, which will just be kernel of D, or the dimension of kernel minus dimension of co-kernel. So this will be an integer. So given any elliptic operator D, I can define a number to it. Okay, any questions till now? This is almost the last thing I need. No? Okay. Okay, so now going to the Atiyah-Singer index theorem. How do I want to say it? Yeah, so let's say Atiyah-Singer index theorem. So first, to state the theorem, I need two things. First will be the analytic index. So analytic index of any operator. So if T is an elliptic differential operator on some bundle E, then I can define index of E, index of D, sorry. And this will just be defined as the, this is the analytic index of E and the differential operator D. Okay, that's pretty simple. That's the analytic index. I will now also need a topological index. This is where it is tricky to define. So here what I want to say is, let's take an element of K theory, which looks like E. Here I want to say it's 0 and not 0. Maybe how do I say? like the trivial bundle, just zero dimensional trivial bundle, and phi. So you want to take a triple on in the relative K theory. So this will be an element of my K theory. What K theory? Hard to say. Okay, so I have to say M and some subset A, right? So this, I want to take elements of this K theory group, but this M and A will be something very particular here. So M will be the cotangent bundle, okay, and A will be the unit sphere bundle. So in the cotangent bundle, at each vector space, just take a unit circle and just patch them together. That will be an open, that will be a closed subset, and just I'm taking that subset. All right. So this, if you take such a K theory and elements of that, what phi is, phi will just be a mapping, invertible mapping from S star M to, what am I saying here? It will be E restricted to S star M to E restricted to S star M. So what you will do is this will be treated as a invertible, this is invertible map, and this will be treated as a symbol. So phi is treated as a symbol. So what I want to say is, given phi, there exists a differential operator D such that the symbol of this is phi. Okay, so that is the analytic, that is what gives the analytic index. But the topological index, I'll just say it's just a theorem, not a very nice thing, but the topological index will be a map from K theory of T star M to Z, which will like do some Thom isomorphism things and use all these and define it. But what I wanted to say is these two are closely related, the analytic index and the topological index. As you see, they can be related using this. And the Atiyah-Singer index theorem is nothing but it's saying the analytic index, whatever I defined, is the same as the topological index. Okay. Okay, so this is not a very insightful thing, I guess, but I'll just give one more Atiyah-Singer index formula. So if I have some nice vector bundle, remember I was talking about characteristic classes. So there is something called a hat genus. That is also a characteristic class. Of E, right? So this is a hat genus. This will belong to cohomology. I forget which dimension cohomology, but it belongs to some dimensional cohomology. What you will do is you will take the cup product of a hat genus with the fundamental class. So probably it was this whole thing. So this will be some nice integral formula. So there is a function here which is sine hyperbolic of something. Okay, so dvol. So this is a very important formula. So if you wanted to compute the a hat index or a hat genus of your manifold or of your vector bundle, you have an explicit formula using the curvature. So this is some function of the curvature. So some function of the curvature you integrate that will give you some this important a hat genus, which is a topological quantity. Okay, so I will stop here. Are there any questions?